Our last lesson about confidence intervals, not confidence intervals, for significance tests for proportions. So we're looking at the tests about the difference in proportions. Starts out with an example about these two people investigating whether the characteristics of the interviewer can affect the response to a survey question. So at a mall, they asked 60 shoppers the question, do you like tattoos? When they interviewed 30 of the shoppers, they wore long sleeve tops that covered their tattoos. For the remaining 30 shoppers, the interviewers wore tank tops that revealed their tattoos. The choice of long sleeve tank was determined at random, and Sarah and Miranda suspected that more people would answer yes when their tattoos were visible. So they summarized the results of whether they just said, yeah, they like tattoos, but they kept track of what they were wearing at the time. So we have the total tank tops and long sleeves, both total 30, but they got 32 yeses and 28 nos. So what we're really looking at is the difference in the proportion of people who said they like tattoos. This difference in proportion is really helpful, especially for a lot of medical trials. So if they're looking to compare prescription drugs, so if they're looking at Lipitor versus some other drug to lower their bad cholesterol, they can look at the proportion of people that it lowers it and see which one lowers it more, or if it's the same proportion for both people, both types of people. For this experiment, we can look to see if something is statistically significant or if there's just a little bit of evidence, but we're looking to see, is there a dramatic difference in the population proportion based off of what we're seeing from the sample. Now, we always start assuming that there is no difference. That's how we did the last set of hypothesis tests. That's always going to be true. There's a write-up on here for how to do this with simulation. We're not going to go through that. If we were in class, I would have made you do it. But this is a possible dot plot from a simulation. This is 100 trials simulated being generated and looking for the difference in the proportion of tank top versus long sleeve of people who said yes. And what this found is 19 of the 100 trials produced a difference in proportion of at least 0.133, which is what these two, I don't know if I ever was supposed to write that out. Yeah, I should have written it out here. The difference in the proportion, there were 18, sorry, I didn't have the right color ready. There were 18 out of 30 preferred tank tops, and the 14 out of 30 preferred long sleeves, which if you subtract those and just use a decimal approximation of it, you get 0.133. So we're looking at how uncommon is that if there really isn't a difference. So what this is showing is you sometimes do get this number or something even larger, but it happens 19 out of 100 times. Excuse me. Which means the p-value would be 19 out of 100. It'd be 0.19, which is not very uncommon. So it doesn't seem like we have evidence to say that it's going to matter, that a difference this large could happen just by chance, just due to random variation. So they don't have the evidence that appearance of the interview causes a higher proportion to say that they like tattoos, as long as the tattoos are visible. So all that to say, we don't have to use simulation for this. We can use this with significance tests. When you do this, there are two main ways that you're going to see this written up. So when you state your hypotheses, they typically have this general form. So we're going to say, we could basically say that the first population proportion is the same as the second population proportion. The main way that we're going to write it up in our notes is that the null hypothesis is talking about the difference of those proportions, just like we talked about when we found the confidence intervals. So they functionally mean the same thing. We're going to write it up as a difference. We are mostly going to be looking for the difference of 0, basically whether we're going to say there is a difference or there is no difference between these two. So for this example, we have a proportion of children we're interested in who are coming to school without breakfast in these two low-income elementary schools. We know 19 of the 80 at school 1 and 26 out of the 150 at school 2. Both schools have more than 1,500 kids, and we're looking for convincing evidence. So we start with our hypotheses, and just like I had written up before, we're going to say that the first population proportion minus the second population proportion, there's no difference. It is what we think might be true. It's just the difference is 0. But we are testing to see not if one's more or one's less, but just are these two schools different? So I'm going to say now that if I subtract these two numbers, I'm going to get something that is not equal to 0. And as always, I have to define my variables. P sub 1 is the true proportion of all students at school 1 who missed breakfast today. And P sub 2, I don't know why I had the brilliant idea to think I wanted to write that again, because I don't. Yep. At school. Oh no, can I not erase? Well, I had a brilliant idea, but it didn't work out, so we're just going to ride over that. Define your variables. It's a pain, but if you're taking the AP test, for sure, define your variables. Always have to check conditions as well. The random condition, the 10% condition for performing a significance test about the difference of two proportions, same exact thing as the test for confidence intervals. The large counts condition is going to be different. So we are going to, I can't remember what I was going to put on that blank. That's frustrating. Wow, I should really know what I'm doing here. I think I just made a typo. Sorry for all the waste of your time. So a significance test begins by assuming that your null hypothesis is true. We are assuming the proportions are equal until proven otherwise. The common value of these two parameters would be P then. We don't know this number, but we can estimate it by pooling our two samples and kind of grouping them together. So we're going to look at the number of successes in both samples combined. And we're going to put that out of the total number of individuals in both samples combined. What that means numerically is I'm going to look at the count of successes for the first group and add it on to the count of successes from the second group and put it over the first group sample size plus the second group sample size. This is going to be denoted P hat sub C. This is the combined sample proportion, but this is going to be the overall proportion in the combined two samples. So we're pooling these together to combine them. So looking back at this two-way table now, we have the school's data for school 1 and school 2. We have their missed breakfast totals or not. Our null hypothesis is assuming there's no difference. If we assume there's no difference, we can estimate what P would be by just pooling these two groups of data. So again, I'm going to take the count of successes from the two groups and put it out of the sample sizes of the two groups. So if I look at school 1, 19 of them said I didn't eat breakfast, but school 2 had 26. That's out of 80 kids at school 1 that they sampled and 150 at school 2. So I'm just going to group these two together and have 45 out of 230. So I'm going to say my P hat sub C, my combined proportion, sample proportion, my estimate for this true value of P is about 0.196, which we could have done without adding any of that. Because I gave you the two-way table, we already knew that 45 people altogether said yes, and we already knew that it was out of 230. So you can get that answer. If you have a two-way table, you can do it with the summations, or you could do it using the two-way table data. It's the same thing. So we're going to use the combined pooled proportion of successes, P hat sub C, when checking our large counts condition, as long as our hypothesis is assuming that there's no difference in the null. So in this case, we're finding the expected number of successes and failures, because again, that's what this P hat sub C is. It's the expected number. So not the exact, but the expected. That means when we check large counts, it's going to look slightly different. So we normally just check N times P. We're doing two different samples, so we're going to have N sub 1. But now instead of doing P sub 1 or even P hat sub 1, we're going to use this estimate. So this is the expected number of successes in the first sample, and then we're also going to check the expected number of failures in the first sample. We're going to do that for the second sample. So the value that you're using for this P location, this proportion, is going to be different this time, but you still always make sure that it's at least 10. That part's the same. So your conditions. The data comes from 2 independent random samples. We talked about that last chapter. It could also just be 2 groups in a randomized experiment. That comes up a lot for proportion tests like this. When you're sampling without replacement, meaning when it's not an experiment, when it's one of these types, that's when you're going to check your 10% condition. That's when you're checking that your first sample size is less than 10% that first population size. And the same thing for the second one. And the expected number of successes and failures of each group are all at least 10. That's what we just wrote out. N sub 1 p hat sub c, N sub 1 complement of p hat sub c. I don't know why I felt the need to make us write this out twice. But they're all going to be at least 10. So in that example with the kids at these elementary schools, we passed the random condition because it specifically said it was a simple random sample of 80. It says a simple random sample of 150. They're 2 different schools, so I can state that it is independent and they are random samples, and then I'm just being clear on what those 2 random samples were stated to be. So for the 10% condition, I'm going to make sure that we have essentially a small enough group. So 80 is actually less than 10%, since there are more than 1,500 kids here. So this is definitely less than 10% of all the students at school 1. School 2 also passes this test. Before we can test the large counts, we need to find that p hat sub c, or estimated or predicted proportion. So that means I'm going to sum, we literally just did this. This is the 45 out of 230 number. We added the 19 and the 28. 26, I can read. So this is when we got 0.196. That's what I'm going to use in my calculations. So I'm going to take my first sample size and multiply this value. So 80 times that turns out to be 15.68. So this one's going to be 64.32. And then I'm going to do it with my second sample size. .4. $120.6. So because these are all at least 10, we pass the large counts condition. So once you meet your conditions, you can go ahead and calculate your standardized test statistic. So to do a test where we are assuming that they're equal, that the 2 population proportions are equal until proven otherwise, we need to standardize the difference in our sample proportions. So that is your statistic. So this is going to look kind of messy, but we're going to first put in our test statistic is still a z value. So in our numerator, we're going to have the difference in our sample proportions. And then we're talking about a difference. This here would be our parameter. But I don't need to write p sub 1 minus p sub 2 because we're assuming it's equal until proven otherwise. So that means I'm just going to put minus 0. That's the nice part. The less than nice part is the standard error of the statistic. When we talked about how we can sum our, what am I trying to say, variances, we'd be looking at this. That's not what I meant to write. However, do not put p sub 2 in these equations. So do not replace p sub 1 and p sub 2 with their predicted values with the hats. So our test began by assuming that it's true that p1 and p2 are equal to each other. So if they're starting out equal to each other, then that means that I can say p sub 1 is equal to p sub 2. They equal some number p. So I'm going to replace every time p sub 1 showed up here, every time p sub 2 showed up here, I can replace them, which I already typed out for you, with regular p's. We don't know this number. However, we have our pooled estimate. We have the combined estimate. That's the p hat sub c. That's what we're going to put in place of p for the standard error in our denominator. So in our denominator, we're going to have p hat sub c, complement of p hat sub c, over in 1, and then p hat sub c. Why'd I put another square root? Complement of p hat sub c over a different sample size. So, and I just realized the exam formula is slightly rearranged. This they factor out because I have the same numerator twice in this standard error of our statistic. So the one that shows up on the AP formula, the numerator looks identical. Actually, I need to pay attention to what I'm telling you about. The AP formula sheet will never give you the whole thing. It gives you the parts. So if you're looking for the standardized test statistic and you're looking for the standard error, your denominator, they factored out the p hat sub c. They factored out the complement of p hat sub c. And so they were just left with the sum of those reciprocal of those two sample sizes. So these are equivalent. This is the one you'll see on the formula sheet. It doesn't matter which one you use because I'm going to show you on your calculator in a little bit, but not yet. So still talking about the kids without breakfast, I want to explain why the sample results give some evidence for the alternative hypothesis. So remember, the alternative hypothesis is just that they're not equal. I think there's a difference is what we're trying to say. So the observed difference in the sample proportions means when I actually subtract the two sample proportions we got, when I take, how am I going to do this? So when I take p hat sub 1 minus p hat sub 2, we would be doing 19 out of 80. That's the proportion from the first school, minus the 26 out of 150, the proportion at the second school. For some reason, I decided it was worthwhile to write out the decimals, but didn't give myself enough space to do so. Oh no, I did. I just didn't plan out what I was doing. So we get this number, which does not equal 0. Because it's not equal to 0, we have some evidence that, hey, the difference of the population proportions might not be equal to 0 either. So we're looking to see, then, this is some evidence. Can we say this is really unlikely to get something like this? This is when we fall to our p-values. Before we do the p-value, we're going to do our standardized test statistic. We're going to use that p hat sub c from earlier. So again, that was the sum of the two success amounts over the sum of the two sample sizes, 150, and that was 0.196. We're going to standardize this. This is that formula I wrote down earlier. So the formula from earlier is p hat sub 1, so what I just wrote out over here. To keep from writing fractions and a fraction and a fraction, if I can avoid it, I'm going to write out the decimal equivalent of this. So 2.375 minus 0.1733. So this, my statistic, my sample values, minus the parameter. We're going to assume it's 0 until we can prove otherwise. All over that god-awful denominator. So down here, we're going to have our pooled estimate here. So I'm going to take the 0.196 times the complement of 0.196 over our first sample size, plus those same two numbers multiplied together. That's annoying. It sometimes tries to autocorrect what shape it thinks I'm trying to do, which I'm not trying to do a shape, but over a different denominator. When I put all that jazz in my calculator, it gives me 1.17. Now remember, this is a z-score. We are talking about something that is approximately normally distributed. So for my p-value, I'm going to my standard normal curve. I'm seeing that I have something more than one standard deviation above, and I'm trying to see, okay, well, that's not super likely, but how unlikely is it to be even larger than this? So your p-value is found either using the table in the back of your book or just normal CDF. Mean of 0 because it's the standard normal. I've already standardized it. Standard deviation of 1. So this is getting me 0.2420, which means this is a pretty common result. Assuming there's no difference, these numbers, this difference in proportion happens 24% of the time just by chance. So because the p-value of 0.2420 is larger than our level of significance, which I don't even remember what they said we were supposed to test this at, 5%. Much larger than that. Because of that, we're going to fail to reject the null hypothesis. Remember, you're always interpreting this by going back to your null. We're going to fail to reject that. There is not convincing evidence that there's a difference in these two proportions of kids who skip breakfast at these different schools. So these numbers, specifically this guy, are a pain to get by hand. So you are more than welcome to just put this in your calculator. However, make sure you don't skip the part where you name the procedure, which I don't think I've even told you the name of this procedure yet, and that you tell the standardized test statistic that your calculator spits out. So you still write down that the answer was 1.17, and you still write down that your calculator got about 0.2420. You can't skip writing those out. So what that looks like on your calculator. Let's see if I got better lighting today. There we go. Okay, so, sorry, my kids were playing with this earlier today. If you push stat, scroll to tests, as we always do. We are doing tests, but we now have two samples that we're comparing. We're talking about the proportion of these two samples, and this is a z-test because we are standardizing it and getting z-values. This is going to ask for the success of the first group, which was it 19? 19 out of 80. We need the success of the second group, 26 out of the 150, and we're just trying to see whether or not those things are not the same. The population proportions are not the same. Just as before, you can calculate it and it'll sketch this area. Ooh, I made a mistake. I'll tell you about my mistake in a second. But you don't have to sketch it on your calculator, so I'm just going to push stat 6 and just make it spit out the values I need. So it confirms that my alternative hypothesis was not equality, so I should have been doing a two-tailed test. I didn't think to stop and check that. I'm getting the same z-score value that we got by hand, and I'm getting approximately the same p-value. It's slightly off because we rounded our z-score before actually getting it. And then it just reiterates what your two sample proportions were, and it also gives your pooled estimate. They just call this p-hat. Not entirely sure why your calculator does that, but it gets you the same thing. So if we go back and find my mistake, I just used a right-tailed test. I assumed that since I got a positive z-score value, it's just to the right, ignoring the fact that way up somewhere here, I wrote out that it's a two-tailed test, which means my answer was right, my work was wrong. It should have been also checking the area below negative 1.177. So this would have gotten me half of the true p-value. I would need to double this. But 0.2420 was the approximate p-value. Nothing else was wrong. I just didn't have my work completely accurate. So when we do this, we're going to have to go through all of our steps as before, and we have our conditions are met. I'm just reiterating that we have our formula for the standardized test statistic. Once we have our pooled proportion, we're going to find the p-value using our test statistic, blah, blah, blah. Let's actually do this. So we're looking at high levels of cholesterol in the blood associated with a high risk of heart attacks. They're trying to see if using a drug to lower blood cholesterol does it reduce heart attacks. So the study recruited middle-aged men with high cholesterol, no history of other medical problems. They were volunteered, but they are randomly assigned to 2 treatments. That's a typo. So we have some of the men taking gemfibrozil and some of them taking a placebo. The next 5 years, 56 men in one group and 84 of the other had heart attacks. Do these results give convincing evidence? So there's some evidence, but is there convincing evidence that the gemfibrozil is effective in preventing heart attacks? So we are trying to test. I'm going to write out the hypotheses, but you always start with just saying there's no difference. So I'm going to say that we're trying to test the null hypothesis that, and I'm not going to use 1s and 2s here. I'm going to go ahead and put G's so that I'm remembering this is the gemfibrozil group. And this is, why did I put an L? PL probably would have been more clear, but whatever. The difference is nothing. But for the alternative hypothesis, I'm trying to first of all say that gemfibrozil is effective in preventing heart attacks, which means the proportion of this group, when you compare it to the proportion of the placebo group, I'm trying to say there were fewer heart attacks here. This group had a lower percentage of heart attacks. So when I subtract them, that means that the difference is also something that's going to be less than 0. I'm saying I'm going to take a small proportion minus a bigger proportion, and I'm getting a negative difference in the proportions. And then always define your variables. It's really tedious, but you can't say this is what you're going to be testing if those are meaningless values. Also, state your level of significance. It's probably given to you in the problem, and you can see we have a low level of significance here because we don't want to have a type 1 error. So then we're going to test our conditions. So these were not randomly picked people. They volunteered for the study, but that's how all drug studies are going to be. They're going to be volunteers. So I'm going to note they are volunteer subjects, but they were randomly assigned, which has to happen. Otherwise, it's just an observational study, and that's not acceptable. So they're randomly assigned to the 2 treatments. So you'll notice I skipped right over the 10% condition because if you're not selecting from a population without replacement, that's an unnecessary condition to check. I'm going to jump right to my large counts, which I'm going to need our p hat sub c value. Zoom in so I can write clearly. So I'm going to take the count. What did I just do? I'm going to take the count of success from one group plus the count of success from the other. This is how many men, and I'm calling them successes, but how many had heart attacks, not quite a success. But it's out of the 2 sample size. So there's 2,051 men in one group, and there were 2,030 receiving the placebo in the other group. So I don't think it's necessary to write this, but I guess it's nice to write my workout. I'm going to be using the decimal approximation of 0.0343. So this is the expected number of successes, expected number of heart attacks. The expected proportion. Now we need to actually check the expected number of heart attacks for our large counts. So first sample size times this proportion is your 2,051. Which is going to be at least 10 because it's 70.35. I'm going to also check the complement. That's not what I meant to write. What do I get? 198,065. And then the same with my second sample. So the expected number of failures for the second group, so the guys who didn't have heart attacks, is this. And I can see that they are all at least 10. So we have passed the large count conditions. We can model this with the normal distribution. So now I actually get to do it. Again, this is the part where you are welcome to jump to your calculator, but I need to find my p hat sub c value, which not what I mean to be writing. I'm going to change my two sample proportions to decimals to make my standardizing equation a little bit easier, which means the proportion in the gemfibrosol group who had heart attacks would be 0.0273. I don't have quite room for this, but the proportion in the placebo group, what am I doing? Who had heart attacks, oh my gosh, is, where'd it go? 84 out of the 2030. So we're seeing that this is a higher proportion. There's some evidence that gemfibrosol makes a lower heart attack proportion, but we're trying to see now if we have convincing evidence. So now we're going to standardize that so we can find the z-score, or just go to your calculator and start plugging stuff in. But I'm going to have my statistic, which is the difference in the sample proportions of heart attacks, minus, we're assuming the difference is 0 until proven otherwise. And then our denominator is going to be using this, the p hat sub c value, so the 0.0343 times the complement of 0. Whatever that was, 7, over my first sample size, and then again with the second. So I'm getting a standardized test statistic of negative 2.47, which is a pretty low z-score. So on my standard normal curve, I got the middle at 0. My standard deviation is a 1. We are way over here at negative 2.47. There's not a lot of area below that. We're going to quantify that by finding the p-value. Ooh, and I just realized I skipped a step. I never stated what test I was doing, which is an extremely important thing to not forget. So I'm getting a p-value, a very small p-value of 0.00688, yeah. So predicted it would be that small, and it was. Up here at the plan step, I left a space for the type of test, but I never wrote it out. You absolutely are expected to write out what test you're using. We are doing a 2-sample z-test for the difference in population proportions. My apologies for forgetting that. So we have to conclude, we have to say what it means that this p-value is so small. So because our p-value of 0.0068 is less than our level of significance, which was really small to start with, we can reject the null hypothesis. We thought we had evidence for it, and we do. So there is convincing evidence of a lower heart attack rate for middle-aged men like these. And remember, this is who I'm talking about. This is not for all men in the population. We didn't select from all men in the population. For the type of men who are in this particular study, if you're like those men who take gemfibrozil, you're going to have less heart attacks than just taking a placebo. Part B on here is just to remind us what the p-value is. Remember, all hypothesis tests hinge on assuming that this hypothesis is true to start out with. Assuming there is no difference, and those are the exact same proportions, which is what I'm writing out here. Assuming that the difference is 0, assuming that's true, and that there's no difference in the effectiveness of the two treatments, this is saying that, I kind of ran into my space, but this is saying that there is a probability, that's what a p-value is, a probability value. I didn't mean to write p-value. There's a probability of getting a difference and specifically difference in the order of gemfibrozil minus placebo, of getting a difference that was this extreme, so, well, a difference in heart attack rates, I guess. Difference in heart attack rate for the two groups. Of negative 0.0141 or less just by chance. So it could happen. It 100% is possible. It's just really unlikely. Specifically, just from the chance involved in the random assignment. If I just somehow randomly happen to put the super duper exercisers in the gemfibrozil group, then what might look like gemfibrozil success is just these particular men's confounding variable, essentially. We tried to control for it by randomness. It's not always possible. So really unlikely for this to just happen by chance, but it could. There is another, oh, I forgot about pointing this out. I already said earlier, we chose a 0.01 level of significance in the example to reduce the chance of making a type error. In this instance, type 1 error, remember, if you reject the null but it was true, then you would be saying, I have convincing evidence that it reduces heart attacks when it doesn't, which would be really, really bad if this drug was given to lots of guys with high cholesterol and you're expecting it to make them better, but you made a mistake and it doesn't actually make them better. I already pointed out that the random assignment is what's allowing us to make a cause and effect relationship. We don't say it applies to everybody because we didn't pick from a larger population, but you can conclude it for these type of people. But I did note in the notes that it can't work for all middle-aged men, it can't work for men of other ages, and it can't work for people who are not men. There's another example on here, but just like the last set of notes, I think it would be really helpful for you to attempt these on your own. I will post the answer key to this along with this very long video, which I apologize for, but at least my kids didn't interrupt me this time. So stay inside when you can, wash your hands, be in good health, and look for more emails from me. And